Hey, Dr. B here again, and let's talk about solids, liquids, and gases. Let's start with solids first. These are molecules that are locked in place and unable to move around each other. They simply vibrate in place. They do not possess enough kinetic energy to overcome those strong forces holding them together. And those forces could be a variety of things, right? They could be metallic bonds, they could be ionic bonds, they could even be covalent bonds. So they have the least amount of kinetic energy as measured by temperature, which is why the intermolecular forces are able to hold the molecules in place. I'd like to add to that by saying that intermolecular forces would certainly be the case if you're dealing with a covalent molecular solid. But in the case of the metallic or ionic solids, there are really no intermolecular forces. Those ionic bonds or those metallic bonds are what's holding it in place as a continuous lattice. Solids are not always more dense than liquids, and a classic example of this is ice, where when it goes into the solid phase, it actually spreads out a little bit and becomes less dense, making it float on top. So there's no quick relationship there. Let's talk about liquids. In this case, the molecules are capable of movement, and there are intermolecular forces. However, they would be fluid in nature. This makes it so that the water molecules can slide around each other easily. So they're not locked in place, fluid intermolecular forces. And at the surface, you may see evaporation. And what's going on there is that these water molecules have a distribution of energies. A few of them, even at room temperature, or a small percentage, I should say, are capable of overcoming these hydrogen bond intermolecular forces and actually evaporating, going from the liquid to the gaseous state. As you heat things up, a greater percentage of them will do that, but even at room temperature, some do. We call this evaporation. Gases, as you probably know, they are much more spread out than in a solid or a liquid. They lack any intermolecular forces entirely. They are usually treated as particles that are bouncing around, don't slow down. Any collisions don't slow things down, meaning they're inelastic. And they have so much kinetic energy that the molecules just bump into each other. The molecules move in random lines in between collisions. And so once you've overcome your fluid intermolecular forces, you've got a gas, and they are very, very spread out molecules. Fine, let's go ahead and ask a few questions. What would evaporated water molecules look like? Well, we're looking at it right here. So we have hydrogen bond forces between these hydrogen in white and oxygen in red. So if you look at this, you always have a plus to minus, where hydrogen's a little plus, oxygen's a little minus. This is a reasonable diagram of these substances. We're not trying to represent a solid. We're trying to represent a fluid, a liquid. So you would have intermolecular forces that are fluid in nature. These molecules would be moving. They can pass each other. It's not like it's locked in place like a solid here. And there would be a distribution of energies leading to a certain percentage of the molecules over time evaporating. So there's our explanation with that Boltzmann distribution. And what makes ice less dense than water? Take a look at that. Give it an answer yourself. Well, I believe the molecules must become more spread out in the solid phase. So when they lock into place in the solid phase, they can't squeeze in between each other like they do in the liquid phase. This gives it actually a lower density for the solid, and it will float. Ice floats in water. You know that you can put your hands right into a liquid, but not in a solid. You can't through the solid. What would explain this? Well, the molecules are locked in place in the case of a solid, but they're not in the case of a liquid. They are fluid in nature. Okay, this is topic 3.3, and this is Dr. B.